approach is yet another translation of the first-field principle, and it will try to select the variable that will have the largest impact in terms of filtering. Okay, so first, some preliminary notations. This is a node of the search tree, so this is a problem with some variables, the domains and the constraints, and an estimate of the size of the search tree. It's an upper bound on the size of the search tree in that case, is the Cartesian product of the domain sizes. Okay, so if you have two variables, x1, x2, x3, each of them has a domain, let's say AB. Okay, AB, AB. The largest possible search tree that you can have is this one. Okay, and so it's really the Cartesian product of the domain. Okay, so you would have 2 times 2 times 2. Okay, which is this search tree. So the largest size of the search tree is a search tree that you will explore if you have no propagation, no pruning at all during the exploration of the search tree. So it's the Cartesian product of the domains. Okay, so we denote by S the size of this problem, the size of the search tree S of P. Okay, it's an estimate, it's an upper bound on the size of the search tree that you need to explore for that specific problem. Okay, so down a branch in the search tree, we will explore sub-problems, and on every sub-problem, we will add a specific branching constraint. Okay, so initially we have the original problem, then we will add C1, okay, this branching constraint, C2, and so on. Okay, so I will denote by CK minus 1 and CK the constraints between two subsequent steps. Okay, and the difference between CK minus 1 and CK is that you have added the constraint x equal to it, so this branching constraint. And we will denote by I. I stands for impact. I of the decision, the impact of the decision x equal to A, okay, is 1 minus the contraction of the size of the search space, okay, between the problem pk and pk minus 1. Okay, so obviously this value is always larger than this one. So this ratio is always between 0 and 1. Okay, and 1 minus this ratio is also a value between 0 and 1. And this represents the contraction of the search space. And so if this ratio is large, okay, so if this ratio is large, it's because this value here is very small. So assume, for instance, it's let's say 10, and this one used to be 1000. It means that now the size of the search tree is 10 after the decision x and is equal to A, and it used to be 1000. So you have contracted a lot the size of the search tree, and so this value should be large. So the closer you are to 1, the more contraction you will get if you would take the decision x equal to A. The problem is that we don't know this ratio of the contraction ratio, the impact of x equal to A. We don't know it, so we need to estimate this ratio. How can we estimate it? We can average the contraction ratio by measuring it on some nodes during the search tree exploration. And on average, we will estimate it like this. This is the average impact of the decision x equal to A over k different nodes. Okay, we measure it over different nodes, and we simply take the average of it. Of course, during the exploration of the search tree, it's more important that the more recent decision should have more impact. And so it's nice to use this strategy to update the impact of the decision x equal to A. This is called exponential moving average. Okay, and so we will weight more the frequent decisions. Okay, so this is the impact before. This is a new decision, the impact that you measure with the latest decision. Okay, and you take this update value for the estimated impact, and alpha is typically a value like 0.9, okay? And so you will take a weight of 0.9 for the most recent decision and 0.1 for the one before. And so you still take into account the previous impact that you observe in the search tree, but the recent one has more impact. Okay, we call this parameter alpha the discount factor in the exponential moving average. So now we can estimate the size of the search tree when trying x equal to a, but without explicitly trying this value x equal to a. It's simply the size of the search tree in the current node, so p, this is S of p, times 1 minus the contraction ratio. Okay, we do this, and we have an estimate of the size of the search tree that we would get if we would try x equal to a. Okay. But this is for the decision x equal to a. What we would like to do is to implement a variable heuristic, so we should want to estimate the impact of the size of the search tree for x independently of the value. And so we can simply sum over all the values in the domain of x of this estimated size of the search tree if we would branch on x equal to a. Okay, we take the sum of everything like this. But what you can observe is that this will be the same for all the variables. Okay, so this will probably not impact our decision on which variable we should branch on. We can get rid of this. And the impact, we can simply define the impact of a specific variable as this sum. Okay? And so which one you should choose is you should select the variable that will minimize this specific value. Okay? We try to select the one that will minimize I of x, which is an estimation of the size of the search tree when you will branch on x. And for the value heuristic, you can take the value a that also minimizes this value. Okay, and so you will select the variable that hopefully will get the smallest search space, and you even select the value that is reducing the most, the size, estimated size of the search space when you will branch on x equal to a. This strategy is called impact-based search.